welcome to the third lesson in Unit 1. Today we're going to be talking about continuity and one-sided limits. The goal of this lesson is to look at how we can determine the continuity of a function at certain points or the continuity on an open interval. Additionally, we're going to be looking at what one-sided limits are, how they're connected to the existence of a limit, and the continuity on a closed interval. Lastly, we're going to be introduced to our very first, what I would like to call hard theorems in calculus, and that's because it has an actual name, and that name is the intermediate value theorem. So in the previous lesson, you looked at evaluating limits algebraically, or analytically is the word that we talked about, and we used some of the properties of limits to evaluate limits. And there were a lot of properties of limits. In this lesson, we're going to be looking at how we use limits to define what continuity is on both open and closed intervals. And we're going to learn about our very first hard theorem, and that's the intermediate value theorem. So continuity. Informally, a function is considered to be continuous at some number c if there are no interruptions in the graph. That is to say, there are no jumps, gaps, holes, breaks in the graph. So some very common examples of where that condition fails, for where there is some hole, jump, or gap. These three examples show a function that is not continuous at the point c, and this is an open interval. In other words, the endpoints are not included in part of the function. So you can see in that first one, there is a hole at C. In the second, there's a jump or a gap. And in that last one, there's a hole, but the function still has kind of a value. Okay. And all three of these examples are going to be examples of where continuity's definition, its true definition, fail. So more formally, we say that a function is continuous at C if and only if excuse me. So more formally, we say that a function f is continuous at C if and only if the following three things happen. F of c is defined. In other words, the function has to exist at c. Additionally, the limit of the function as x approaches c has to exist. And lastly, and most importantly, the value of the function and the limit of the function have to be the same. And it's really important that you know all three parts of this definition, because on the AP exam, you may be asked whether or not a function is continuous, and if so, or if not, what part of, or how do you know that the function is not continuous? And they'd be looking for one of these three parts of the definition. So, let's talk about the existence of a limit, since that's part of the definition of continuity. So formally, we say that a limit exists for some function f if the limit from the left and the limit from the right are the same. And so, as you can see here and here, these two pieces of notation, the small minus sign and the small plus sign, indicate a direction that the limit is being taken from. So the small minus sign indicates that the function is being evaluated, its limit is being evaluated from the left. So as an example, consider the function square root of 1 minus x squared. Those of you who remember things from geometry and graphing circles will recognize this as the top half of a circle, centered at 0 with a radius of 1. So the question is, does the limit of f of x as x approaches 1 exist? So the limit from the left exists, and it's equal to 0. So as you can see from the graph, as we move from the left and get closer to 1, the graph approaches 0. However, if we come from the right side, the limit doesn't exist because the function doesn't exist. There's nothing to the right of 1. So we would say that for this function, the limit as x approaches 1 of f of x does not exist. All right, so now on to the meat and potatoes of this lesson. So this is really the first big theorem that we talk about in calculus, and it's a really important one, but it can seem overly simplified sometimes. So today you will engage in an activity that has you exploring some of the ways the intermediate value theorem can fail and the reasons why it's important. Okay. So first, let's talk about the definition. The intermediate value theorem I have written up. If f is continuous on a closed interval from a to b, and f of a is not equal to f of b, and k is any number between f of a and f of b, then there's at least one number c that is between a and b such that f of c is equal to k. Now, we're going to talk about a lot of theorems that sound like this, very mathy, very rigorous, and I'm going to do my best to try to break them down in layman's terms. Okay. Graphically, what this says is if a function's continuous and there's some number k that's between two outputs f of a and f of b, there has to be a number c that will take me to k, and that number c has to be between a and b. That's really all of this function says. And in layman's terms, excuse me, we could say that the IVT, which is short for intermediate value theorem, guarantees that there is a number between a and b that's going to take me to k, as long as the function is continuous. And this is, like I said, a very important theorem that's used for proving other theorems in the future. So let's look at a quick example. We want to use the intermediate value theorem to show that the given polynomial function has at least one zero on the interval from 0 to 1. So we're going to use this function, x cubed plus 2x minus 1. It's a polynomial function. And the first question that we should ask is it continuous? Because that's part of the hypothesis of the intermediate value theorem. And in order to state the conclusion of any theorem, we must show that the hypothesis, or hypotheses in this case, are true. Well, it's a polynomial function, so it has to be continuous over its entire domain, because we know polynomial functions don't have any jumps, skips, gaps, or holes. So check. What's the value of k that we're interested in? So the value of k is some output value, and if we reread the question, 0. We want to know if there is some number between 0 and 1 on the x-axis that will give me an output of 0. So 0 is the value that we're going to let k be. So the next thing we need to ask, the next piece of the hypothesis, is that number k between f of a and f of b, between the endpoints of the output of the function? Well, substituting in 0 and 1 from the interval, we see that yes, 0 is between -1 and 2, and therefore k is between f of a and f of b. So both conditions of the hypothesis of the intermediate value theorem are met, and therefore the conclusion can be made. That is, therefore, by the intermediate value theorem, there must exist a number between a and b such that f of c is equal to k, which is 0. Okay? And it's very important to remember to make your conclusions in this type of format. It doesn't have to be worded exactly, but you want to state the theorem that was used, and it's important that if the theorem, which most theorems have, has a hypothesis or multiple hypotheses, that you are showing the work to indicate the truth of those hypotheses before making those conclusions. So, in quick summary, continuity has a 3-part definition that does involve a limit. For a limit to exist, it has to be true that the limit from the left and the limit from the right are the same value. Function may have a limit but not be continuous, but not vice versa. And the intermediate value theorem states that every point in a continuous function's domain is mapped to some value in its range. Thanks for watching.